All right, I guess we'll get started then. So, hello everyone. For those that don't know me, I'm Alexiy. And today we're going to talk about world foundation models. And this sounds really scary, but basically the TLDR of this is basically, what if we can basically learn a model to predict the future state of the robot given its action, right? So you can think about this, if I'm here, like as a human, right? If I move here, I can predict, okay, I'm going to move right, right? And this is basically the same idea, can we learn a model given a robotic input? If we move, right, how will the world look around us, right? Hence the name World Foundation Models. All right, sick. Also, before why are you saying to dismiss? Okay. Also, that's very, okay. Anyway, so before I move on, just feel free to ask any questions whenever. I just want, it's feedback from me, right? Because I know, okay, maybe I should go in on this, right? And then, again, it's also, open to discussion, right? This is, super informal. This isn't, a 300 people lecture hall. So anyway, so this is basically a formal definition of what we're working with. So again, it's really hard. We want to basically train agents virtually, right? We have a simulator, we want to leverage it, right? And instead of that, versus compared to training in the real world, right? And at the end of the day, we want to have a world foundation model, basically, which is at the end of the day a fine-tuned VLM that will basically function similar to LLM. So in this case, you're given your prior observations, right? So think images, right? Joints. If I say joints of a robot, do people know what I mean, right? The angles of the actual manipulator, right? That defines your state of your robot, right? It's a 0 or 1, whether you're holding something, right? And the current action of the robot, in this case, trajectories, text description, literally anything, right? And the whole point is you're trying to predict the state of the world. Yeah.
Good question on notation, because I did it also in this email. Is there a difference between X hat and X0 without a hat?
Yes, that's a good question. So anything with a hat means it's predicted, right? So if I had if I have X hat T, right, that came from my model, right, versus XT, right, that's the actual ground truth.
We have simulator environments that will do this exact thing, right? Where I give it the state, or I give it the state of the world, the robot does some action, and the result of that is xt plus 1.
Yeah.
Right? Why do we need a VLM to simulate a simulation?
Good question. Well, it's not really a VLM. You can do it I guess the better example would be just a GAN. So basically the whole point is that if you are operating in the real world, right, where you can't just take the real world and put it into a simulator, right? What if you can just predict how the world will look like if you take an action, sidestepping the simulator?
I don't understand. In what scenario can we not use a simulator?
If it's hard to reconstruct the world, for example, right?
Okay.
That's the whole point. And the whole point at the end of this, that's one example, right? In reality, this is it's not really. That's one of the applications, but another can just generating data, right? I give it a text description. Give me a video of a robot lifting a box. Right, and it will generate videos of a robot lifting a box.
And why can't that happen with a simulator?
I think it's more of just a synthetic data thing. I know for cars and stuff, it's good just to for you're trying to you can use a simulator to mine a lot of out of distribution data, for example.
Well.
Actually, you can do that at the simulator too.
Yeah, that's a good point. I don't know. I guess that they just want to show this. The whole point is maybe there are some environments you can't really capture in a simulator. I don't know.
Okay.
Realistically.
Okay.
Yeah, that's a good point.
So this looks like it's a discrete time process. Does there exist, just out of curiosity, continuous times analogs of this?
I don't think so.
Okay.
Yeah, it's all I see past t frames of video and I predict the t plus first.
Okay.
All right. Cool. Good questions. Yeah. Gina, that's a good question. Why you can do it? I don't know. I think this also realistically this is also NVIDIA just flexing what they can do. So we have GPUs. What can we do? So anyway, the whole point right now is it's a way of generating data. Right? So in this case, the input to the World Foundation model was basically a visualized trajectory. So these are actual points, and then the frames. Can you see my mouse if I move it? Nice. So then the actual frames are basically what was generated by the model. So that's an example. But then again, you do have a point. Why don't I just yeet this into a simulator and ask it to generate the same thing? My biggest thought was it might be a little bit more realistic because the VLM was pre-trained on the real world.
Okay. So it's pre-trained on the VLM is pre-trained on the real world and then fine-tuned on a simulator.
Fine-tuned. It's fine. It's not trained on simulators at all. It's pre-trained on videos of like actual robotic tasks.
Okay.
So maybe it might like capture some more realistic parts. Again, I don't really have an answer to your question there. Yeah.
Is it possible that it's because the way that cameras are made, like they have some imperfections, and like, for example, they have some circular imperfections. I know those are changed afterwards that aren't perfectly represented by a simulator.
Well, if you have circular imperfections, maybe you're trying to. Yeah, you can also as you can also again. It's a good question. Why not just use it into a simulator?
I mean, if you look at like Microsoft Flight Sim, it's so realistic. Like you could sometimes not even tell the difference, and that's a game engine, and that's like designed to be not super graphics intensive. This is NVIDIA.
I guess
stacks and stacks and stacks of these things.
The problem is, I do know that if you want to make like realistic scenes like those, it takes hundreds of hours. And like, that might be just more computationally inefficient than just going outside, despite the fact that we're CS majors.
yeah. So
these environments are still simulated environments, right? They're like real world.
the data is from real world. The data that you train the sonnets is from the real world, but the data you generate, so the images that you generate, are purely synthetic. They don't exist.
So the environment is like synthetic.
The data that you're outputting is synthetic. Think of it as like a video generation model.
So it's Sora, right?
Sora.
Plus you can interact.
You can think of it as Sora in the robotics context.
Okay, I'll let you continue.
Yeah. So Cosmos is a massive paper. It talks about how do we actually get the data, how do we then tokenize it, and again, this is a very common idea. We first want to give a massive pre-training base model, which is if you think of it just like if you download Llama, right? That's just the base weights, and then we want to post-train it on the robot-specific task using high-quality samples, and then finally the guardrail. So today I'll basically see if I talk about the first four, and then we'll just see how we go and adjust. This presentation is pretty long, so we'll just see what happens. So kicking us off, the biggest problem in robotics is there's not enough data. And although you see 20 million hours, that's still realistically that's not enough to actually get a very good understanding. And the whole point is that if we have limited data, we want to get a very good a very wide range of it, right? We want to have basically in our pre-training phase, we want to have a very robust model. So in this case, as you can see, these are just again some samples of where data came from. And again, this is just raw data, right? So for example, if you have a video, right, you want to take the video and you want to split it up into 3-second intervals, right? Then after you split it up, you want to filter them, right? You want to deduplicate them, right? If you have a copy of a video from two different locations, they're the same, you want to remove one of them. At the end of the day, they have 10 to the power of 8 of pre-fine tuning clips, and then finally they have a 10 to the 7th of just high quality post-fine tuning ones. Cool. This is, I guess, so again, the whole point of Cosmos is that they have if I say foundation models, just implied it's a world foundation model. So they have basically two foundation models. One is a diffusion-based one, and that uses a continuous tokenizer. And the other one is the autoregressive one, which is similar to just a standard LLM, and for that we need discrete tokens. And again, the pipeline goes, you have your input video, right? You have to then go ahead and split it up into actual tokens, and then do something with those tokens, right? And then you want to basically regenerate them through a decoder, and then reconstruct the video. Yeah?
So there's a question about using analog time. Do continuous tokenizers, or how do continuous tokenizers work?
Yeah, that's a good question. So I don't think they're not there are existing tokenizers, but we'll see later, one of their transformations, it's trying to encode that continual example, that continual, basically structure of the data. But at the end of the day, you still have to think the input data is still finite, right? We're still feeding 60 frames per second, right? Video. So I don't think a lot of the stuff that they work with are just I have my raw video. How can I basically transform it into a better basically a better representation that basically holds that more of the continuous data. But as far as I know, it's still discrete.
So here they work with videos, some sort of representation of the world, an abstract representation of the world.
What do you what do you mean by abstract? You have your input video, right? Things it's a robot going ahead and lifting a pen, right? What do you mean by abstract representation?
Trying to keep track of where everything is around you.
You can think of it that way. It's basically just you're trying to have a lower dimensional representation of the raw video.
Okay.
Yeah. Yeah.
Can you explain the difference between those?
I'll go into it.
Oh, okay.
Yeah. Okay. So this is just adding some more full formality. We're given our input time steps, like video frames, right? Standard image data. Again, if anything here, want to go slower, let me know. We have our encoder, which takes basically our images, right? We go ahead and we're going to encode them into a lower dimensional space. Again, the key thing here is that we're still operating over 4D, but basically the whole point is that we're decreasing the time, height, and width and channel dimensions. Time, height, and width dimensions. You might scale up a channel dimension. And there are decoders. Its job to basically reconstruct the images from the output of the encoder. Yeah? Okay, sick. This is basically how it looks like. Ignore I think I go into higher wavelength net. Yes, I do. Okay, so this is basically a transform that they use to basically encode and basically. Oh, I see. I should not have put it sideways. That is my bad. It was sideways. I know. I'm just looking at it to see everyone just Okay, yeah. Sorry, that's my bad. We'll go into every single one of these sections one by one. It's so funny. Oh, you're gonna just this. Okay, we'll go into one by one. So basically, wavelet transform. Think about it this way. Right now, just think 1D. Right? We have a set of basically video frames. Think of just 1D a signal. You have V1. Right, V4, right, just 4 image frames, right? Now, just think when I say a signal, just think just one dimension, just understand how this works. And what we do, there's basically this cool basis, which basically converts you from your, when I say basis, do people understand what I mean? Everyone here has heard of basis or linear algebra, linear transformations, yes? Sick. Okay, so basically we're going to define this basis that will, standard basis, and as your standard, 1, 0, 0, 0, 1, 0, 0, and so on, right? And then we're going to find a way of basically transforming it from your standard representation, just think of a signal V, right, to a different representation. And again, this is just the change of basis matrix that you happen. So basically, what we're going to do is go back, yeah. I'll explain into it how it works. I'll show you why it works. Yeah.
Why is this good? Why do we want?
I'll explain.
What is the meaning of a long signal?
A what?
It says compress long signals into smaller ones. So when you talk about videos, does it mean
Think of a video as a sequence of frames, and that's a signal, right? You can think of it think of a 1D video. Think of 1 dimensions for now. Yeah.
Okay, so long signal just means either too much, a tall data frame, or
maybe I used the wrong words, but the next slide. I hope I'll explain on the next slide. Keep your question if I don't answer it.
This is your basis, right? This is your transformation matrix.
Yes, correct. So you just keep questions in mind. So this is just an illustrated example, right? So in this case, suppose that our video, and again, right, just think 1D, right? The whole point is that we have this idea in 1D, and we're going to generalize it to images, right? So think of and you have your image 1, image 2, image 3, image 4, sequence of videos, right? Let's just say, just for now, think 1D, right? 6, 4, 5, 1. Right? This is basically a transformation where we take our image, right? So now again, if we take the inverse, we're now converting from our world frame, so from E to W, right? The hard representation. And we're basically, this is just I think a hack. I don't know how they actually came up with this, but just the actual way of how this matrix works, if you look at the actual transformed output, how it looks like, you will observe that C1, right, the first index in this vector, is going to represent the average value of the signal, right? So if you sum all these values up and you divide them by 4, C4 will represent the average value, right? Then, if you look forward, you'll see that C2 will give basically the coarse view. I don't know what the coarse view means when I looked into it. I think it's just an additional value you can just tack on. And then C3, now what you're having is, you have your V like this, right? So you have V1, V2, V3, V4, right? And then this, again, this is going to be converted to C1, right? C2, C3, C4. Right, C1, right, will capture basically all the average information in the full length of the signal. So think you're capturing the average information in the full length of your video, right? Then we're going to have C2 is going to capture the average information in the first 2 frames, right? Similarly, C3. I misspoke. C3. Similarly, C4 will capture the average information in the last 2 frames, right? You can think of this as basically a PCA. Right, but just in signals, right? So basically taking your image and you're decomposing it such that if you go through the order, you have more important information at the start and less important information at the end. So what we're going to do is, we have like, again, at the end of the day, we're working with image data, right? And that's a lot of information. So through this transformation, we're going to go ahead and say, let's just get rid, again, this is just 4 frames, right? This is 4 frames, and right now, just one dimensional, right? In reality, we're working in 3 dimensions, right? We're going to basically go ahead and get rid of half of, basically we're going to compress it by just cutting half of the information, which in this case it's this. We're just going to basically get rid of it, and we're going to left with just C1, C2.
What is C2 again?
C2 is, I should have looked into this. It says that it gives the coarse details of V. My thought is just like, it says like, like which side is bigger. But I don't think that's it. Like basically like if you like tack on one, like again, you're trying to reconstruct it, right? So like if you just, again, we're starting off with C1, right? So it's going to be like 4, 4, 4, 4, right? Just C1, just the average value, right? Then V, I'm assuming is going to tell you like, which side is like weighted more. C2 is like which side is weighted more. But I'm not too certain. I did not understand also what they said by the course, the details and the coarse details of V. I saw what they were doing with like C3 and C4 because you start like describing the details in like the other parts of the input. Yeah.
So why is that operation like the inverse? Like why isn't just the projection like V type V dot T W?
V dot T.
Like to get C, you're taking T inverse dot V, right?
Yeah. So basically V is it's our raw image, right? And
so why is it the inverse that you're multiplying?
Well, because we define it this way, right? The transformation, because this transformation is taking us from W to E. We're going from the image in the hard basis, right? From our hard basis to our standard basis, right? So now we want to convert from our standard basis to our hard basis. Does that make sense?
Okay.
Yes? Is everyone following there? We have V, which is a representation of our image in our standard space, right? So real world, right? And we want to convert it into representation that's basically ranked in terms of like a PCA. If I say PCA, if that does not make sense, then just focus on what I've talked about before. If you know what it means, that's basically what this is doing. So you're taking your image, right, which is in our representation. We want to convert it into the Haar basis representation, right? And the whole point is that also like this matrix, it is invertible. So it's bijection, so you're not losing any data. Okay? And then, so now what we're doing is that we're going to apply this 4 times. So we're going to apply it once, right? So we're going to have like V1, V4, apply it once, we're going to get V1, V2, right? And apply it twice, we're going to get like, I don't know, like V1 prime, V2 prime. Oh, it's just V1 prime. Right? In reality, again, it's not just simple, just like 4 image, like just similar things. It's just like a simple example of how it'll work. Cool? We're all still good?
What is the meaning of first part of V, second part of V?
Oh yeah, good question. So the first part of V is like if you have like V1, V2, V3, V4. This is the first part, part 1. This is the second part, V2. Right? So, yeah.
How did you come up with the Haar basis?
I did not know how. I tried to read into it. I could not understand.
So it's a trust me.
Yeah. Yeah. I tried to understand it. Okay, cool. So now again, we have our image, right? And you can see it here. Right? So you have like these like 4 frames, right? Again, we're doing a 4x reduction through this, right? So we're going to convert into like these intermediate frames, right? And then now we want to have basically a local attention, right? And we achieve that through convolution layers, right? So we're going ahead and we're going to have a 2D convolution, right? If I say convolutions, everybody knows what I mean, right? Okay. Okay. I see nods. Hand? You're good? Okay. I thought you were ready. Okay. Cool. So we're going to have 2D convolution for actual spatial attention, right? So like basically in a single time step, right? In a single image frame, like what information is near me. And then we're going to have 1D convolution, which is, okay, across a single basically what is information across a time dimension in a single point in space. And finally, we're just going to add an additional, they throw in the spatial and temporal attention, and it's basically of like, okay, if, I only want, it's kind of like a mass attention, so I only want the future frames to like only attend to the ones that are before me. So, right, you can see like, sorry, question?
So I was trying to understand what exactly the C1, C2, C3, C4 are doing. So I just computed the inverse of that transformation matrix, so you can maybe write it out But it makes it very clear, the averaging part, the course details I don't know, but you can...
Okay, I can type it out. Okay. Yeah, and this is good. So basically, again, 4x4 matrix, we're going to have 1/4, 1/4, 1/4, 1/4, 1/4, 1/4, negative 1/4 is negative 1/4. Yeah, 1/2, negative 1/2, 0, 0, 0, 0, 1/2, negative 1/2.
So if we compare it to the C1, C2, C3, C4 descriptions on slide 14, like we can see how C1 is just average of all of them. C2 is course details, so positive of first 2 frames, negative of the other 2, and the first detail second part.
This is really cool. Yeah, thank you for that. Yeah.
Yeah, this matrix is like way more intuitive.
Yeah.
I mean, it's not your fault.
No. They think you know.
Yeah.
No. Like that's what that's good. Like, don't be like, oh, I'm gonna point something out that he's gonna hate me and ban me. No, I won't do that. I won't. I'll cry tonight for not doing this myself. Okay. Anyway, does that clear stuff up for people? All right. Sick. Nice. Okay. So, and then finally, again, spatial temporal attention. So you can do things like masked, right? So we're only going to attend to the frames that came before us. So using this, again, this is basically, please don't tilt your head sideways. This is basically what those are basically the 3 things that were explained. So we're going to apply this for encoder n times and for decoder n times. And then now, we're going to have, again, we have 2 tokenizers, right? One that's continuous for the,
Wait, stupid question, what is n?
And, yeah, that's a number of blocks. So you have, like, these blocks are repeated.
Okay.
Great question. Good. Yeah.
You said there's 2D kernels and 1D kernels?
Yeah.
In the image on the right, are they like one after another or are they in parallel?
They're one after another.
Okay.
Yeah. Casual resampling. Causal resam block, downsampling. Yeah, so this is the 2D, this is the 1D. I'm pretty sure, yes. Okay, so now, yeah.
I'm sorry if I missed it. Could you explain spatial temporal attention?
Yeah, it's basically mass attention. So basically, see how these lines are here, right? So you're basically like, if I'm like, like the embedding 1, I'm masked out to only attend to, I think it's just like a transformer attention, basically, that they tack on.
But of sequences within the video to the other sequences, like that?
It's self-attention.
Right.
Yeah.
Okay.
Yeah, and then you're masked, so you can only attend to previous frames. Yeah, see, self-attention. Okay, so again, ask questions, right? I don't care if it's like, I have no clue what dim means. Like, just ask, like, because like, if you have it, like, people also have it, okay? So now, again, the output of this is going to be a spatial latent space, right? So we're going to get a sequence of, we're going to sequence of tokens, and they're each going to be like dimension 16. So again, that's fine, that's continuous, right? But now, we want to have discrete tokens in the case of the autoregressive model. So what we're going to do, we're basically, yeah.
So once you go through the regress block, the downsample, the temporal attention, whatever is the output of that is what you're trying to reconstruct with the autoencoder? Is that?
Yes.
Okay.
Yes, correct. So now, again, we're down to dimension 16, but then, we want to project that using basically, and create discrete tokens out of it. And we're going to do that using something called finite scalar quantization, right? And then they're going to get 64,000 word vocab size, right? And like, here's a good example, right? So basically, the whole idea is that here, like, again, your output is only 3 dimensions, right? Here it's 16, right? 3 dimensions we can visualize. And what we're doing is that we're basically saying, okay, if I map to some continuous point in this space, I'm going to basically project myself to the closest discrete point. So we're going to take every single, basically, dimension, we're going to discretize it into finite chunks, and then we're just going to project a point to, like, the closest discrete point that we've matched. Yeah?
What is the closest point here? Is it Euclidean?
Euclidean, yeah.
This tokenizer, how is this connected to the hard basis that we talked about earlier, the wavelet transform?
Yeah, so the hard basis, the first step in it, is basically a way of downsampling the video to most important information present.
Okay, so you downsample a bunch of images or frames first, and then you again downsample them?
So once we downsample them, once you downsample them, like the number of tokens is fixed. Right, so you can see it here. So you have a G1 through G4 is after the wavelet transform, right? And after that, the number of tokens is fixed. We're basically just making sure that they can, like, all information is, like, we were adding basically local and global attention through local attention through the convolution blocks and global attention through the self-attention mechanism.
How will the wavelet transform work if you only provide one image?
One image? Basically, that's a good question. So one image, it'll be transformed. Again, you're still going to go through the Haar wavelet transform, right? But then you will only have the 2D spatial attention, like the 2D convolution by itself. Because there's no temporal, right?
That kind of sounds like a dumb question, but if you hear like all of the videos they had, you said 20 million hours, they must not have the same like input dimensions. How did they go around that with this? Did they do different types of 2D kernels?
It's a good observation. What they did is that they kind of cheated. They they grouped it into like 5 fixed image sizes. So they did image ratios, right? I think it's like 1:1, 4x3, right? 3x4, and I think like also like the 9x16 case.
I see.
Yeah. Okay. So now I'm just throwing this up here again. I'm not gonna try to go into them because I don't understand some of them. But the first stage is that we're just trying to basically make sure that we're conserving all the information, right? So in this, if I say VGG, do people know what I mean? Okay.
Like the feature extractor?
Huh?
Like the feature extractor?
Yeah, so VGG is basically think of it just like if I say resonant, people know what I mean. So think of VGG as like something that builds on top of our resonance. It's basically an image encoder, right? It's an image encoder that has like, again, you know, like if like you have like a standard resonant, right? You have like your image, right? It goes, can you guys, no, you can't see. It's very sad. Okay. You have your image, right? It's going to go into like a resonant block, like following in addition with the skip connection, right? And you're going to repeat this n times, right? In this case, it's L times, right? And this is basically the L that is happening. So repeating this L times in every single point, you're comparing, okay, is the encoding of my output image frame the same as the encoding of my input image frame? And you're just computing this loss over all basically blocks of your, in this case, your VGG, over all time steps. And then finally, there's also the scalar alpha L, because like I don't know how they computed it. Things just like they just chose it to be like you know, you probably want to weigh some parts of the encoding step more than others in the loss. Yeah.
I'm confused about why they have used L1 for all of these.
L1, what is?
Like the one norm rather than two norms. So it's,
Oh, that's a good quiz.
it will encourage like sparsity, right? Why is that a good? Why is that? What is the like? Why is that the intended behavior versus L2?
Sorry, can you? I'm not too sure about like what happens like with the trade up between L1 and L2.
Do you know? Have you seen that diamond shape versus the circle shape when you're trying to?
Do you want to be on? Just look it up real quick.
Yeah, search L1 versus L2.
L infinity.
Or L infinity is like a
just
like a rectangle. Oh yeah, exactly. Images they probably have a diamond. Oh yeah, exactly that one. So
No.
Oh, wait.
like the,
Okay.
but it's actually good.
Okay.
That's
So L1 is
yeah. L1 is the one on the left.
okay.
So it encourages sparsity where
What is sparsity?
like B2 will be fully activated, but B1 will be 0.
Okay.
Right? In this case, in the right case, it is going to be both of them will be partially activated. It could be
I
one
see.
but it's
see.
unlikely for that to happen.
Oh, I see.
by
That's neat.
default.
That's neat.
So
I don't think I can answer that. I don't know. Yeah. This is cool though. It's a cool visualization. Okay. How do I go to full screen again?
that double arrow on the right, and then presentation mode. First option.
Thank you.
Isn't it that it's just like one of them has median versus average?
I have not thought about it like that.
Because L2 is average and is mean, and L1 is basically median of data. So it's not at all affected by fixtures.
Oh,
So
I-
that's what we would do.
I don't think.
So I have a question. Why do we need to compute the loss by computing like the features first? Why can't we just like subtract them?
Yeah, that's a good question. So we could subtract, like by basically you're asking why do I have to pass it through my VGG network instead of just taking my input image and output image and comparing it, right? Well, the idea is that we want to basically like every single time you go into a future layer in your VGG, you're getting basically a more what's the word? It's basically like it's a more refined representation of it. Like not refined, but like it's like Basically, it's like, you know, have you seen like the video, like at the start you have your image, right, and it's like slightly distorted and all the way down to like some internal representation,
Like I've
right?
seen, like, those
Yeah.
convolution
So
versions.
basically, at the end of the day, you want to make sure that you're the same, like your image holds the same information at every single point, right? Because at the end, you're interested so that your final block is most representative.
But how would that not encourage, like, because like the pictures we ended up seeing, I mean, I'm sure there's a lot of steps afterwards, or like very realistic, like photorealistic.
Yeah.
But I feel like if you're just comparing like the feature vector from the VGG, then you might come up with some like weird garbage which sort of encodes the features, but it doesn't look right.
No, it's the minimum of the.
I think like the whole point is like you're just trying to add like additional loss terms. Like, you don't want just like, you know, like miraculously, you know, like just like your input and output image, right? You maybe want to give your model some more hints of like where it's getting close, right? Because you'll start with an internal representation, you want to build outwards, right, through the VGG maybe. Yeah. Okay. On top of this, we have an optical flow loss, which is just, you know, optical flow is basically like, you know, if I have an image, right, with like, you know, like a circle here, right, and an image with a circle here, right, I want to make sure that that's consistent. And finally, there's also just some loss for reconstruction of images.
What is XHAT here? Is it the output of your
Yes.
the model that we talked about earlier?
Yes. It's the output of the foundation model. Okay. And this is basically the result after training. So signal to noise ratio, higher is better. You know, we want a higher signal, lower noise. So Cosmos' tokenizer also like really like basically these represent like different what do you call it? Like different like resolutions. So like basically like the output of tokens. So here you have 8 by 16 by 16 versus 8 by 8. So yeah, pretty good. Okay, so now we're going to move on to basically diffusion. So we have two models here. We'll see which ones we go over, but diffusion, I think it's like the more fun one. So yeah, again, questions are good, questions are encouraged. Yes? Okay. So again, the whole point is that, again, if I say diffusion, people know what I mean. Like think like image generation. Do people know? Okay, I'm seeing some nods. Okay, so think about it this way. I want to generate an image of a cat, right? I'm going to start with like some noise, right? I'm going to condition it on like, you know, an encoding of like, I want an image of a cat, right? And then basically, I'm going to go through like a certain number of like basically like denoising steps, right? So basically, you're going to go from like xt, right? Which in this case, like an image of like, thank you. I can't draw a cat, so it's going to be a stick figure. So it's going to be an image of a person, right? And then we're going to basically, the forward process that we're basically removing noise from the image. We're destroying it, right? So now, like, in some person it's a little bit more distorted, right? All the way, right, to x0, right? Where we just have like just random noise, right? I think, actually, let me just like quickly Google this. This will make sense. Diffusion example. Images. No. ML. This. Please don't make me give you my soul when I log in. Okay, this is what I'm talking about, right? So this is the forward processor. We start an image of a human, right? Oh, I messed up the time step. So image of a human, we denoise it, right, over key time steps, adding incremental noise every single time through a Markov chain. If that's scary, don't worry about it. And then finally, we go ahead and we are trying to learn the backwards process, right? So the forward processor, we're destroying the image. Backward process, we're trying to reconstruct it. So that's diffusion in a nutshell. I see a question.
So what did we achieve by the tokenizer?
The tokenizer, because you're going to do this diffusion process over the tokens. You're not doing it over the raw video frame.
No, but the tokenizer, like the output is also the image, right?
Yes. So so basically the process is you take your image, you take your videos, feed them through the encoder, get the actual tokens, do the diffusion process over the tokens, and then feed them through the decoder of the tokenizer.
But you get the image back, right? Because
Yes.
you have an autoencoder, so the decoder decodes back the latent representation into images.
Yes. So think of it this way. I have my encoder, right? I get my tokens, right? Here, I do diffusion over the tokens, right? I spit out the tokens, right? And then I basically feed them through a decoder.
So the diffusion process is between.
The diffusion happens over the tokens.
So after encoding your. Okay.
Yes.
But then what's the point of getting? Okay, it's clear.
The point of it is that you're reducing the dimensions over which you're doing the
I thought
diffusion.
this diffusion is coming after the decoder.
Oh, okay, cool. Very good. Okay.
Just the encoders are fixed length, no matter what the input is, right? Is that the idea?
I think they're variable length. Because if you look at the encoder, what's happening is that we're doing the hard, like basically like if you have more like by fixed length, you mean like fixed temporal length or fixed height width?
Fixed height width is like,
Well,
the idea is like when you do the diffusion, like is the diffusion model the same all the time? You just do it on one input output, or do you have to do it like separately?
The input to the diffusion model, it's basically like a fixed set of tokens.
Okay.
Yeah. So I think they constrain to like 32. Or something like that. I'll have to slide it later on. Okay, anyway, moving on. So the objective of denoising is that you're sampling a data point. Think of it as sampling. Right now, just think of images, right? I'm sampling an image from a distribution, right? And then I'm sampling a certain basically set of noise, right? What I'm doing is that I'm saying, okay, if I take this image, tack on the noise, right? I want to make sure I pass it through my decoder. I want to basically have the decoded image be as close to the original image as possible. Right? And then I'm repeating this over the n time steps. And what the modification that we do here is that, okay, originally we this is going to get a little bit complicated, but basically we're going to have basically lambda of theta again. So not theta, lambda of sigma. Lambda of sigma is basically it's a weighting function, right? So basically the whole point is that the amount of noise I add, I want the weight of that data sample to change depending on depending on how much I've trained, right? So at the start of my training, right, I want there to be equal length, equal weight from all the noise that I add, right? So whether I add a lot of noise, whether I add a little noise, I want there to be equal contribution to the loss from that sample. As training progresses, I want to change that. I did not look into how that changed that, but that's basically the overall idea. But the whole point is that on top of that, we're also going to tack on mu of sigma, which is, think of it as like basically another classifier that says like how certain that you are that I can actually denoise this image, right? And the idea here is that, okay, if the MLP gives you a high probability that, hey, I cannot denoise this image, right? Then I'm going to scale down the contribution from this loss. Does that make sense? Yeah.
How is that MLP treated?
I did not look into that. Yeah, they say it's an MLP, but I was actually also surprised. I was thinking it would just be like another something more complicated. Does that make sense to people? Right? Just like run this through. Right? Think of this lambda of sigma as fixed. Right? If mu of sigma is high, right, then e to the mu of sigma is going to be high. Right? So therefore, this loss is going to be low. Right? The loss from the denoising. Right? The amount of error I had in my image. Right? Conversely, if this is low. Right, this is low, so I'm going to higher contribution for my denoising loss, right? And then we tack on the loss from mu of sigma because we want. We tack on the mu of sigma to actually basically discourage the model from saying, oh, I can't classify anything, so I'm just going to output that I can't classify it, and then this is always going to be 0, right? Make sense? Okay. If you're confused, right now, don't hesitate. Ask a question. I'll gladly answer it. Okay. Cool. So now again, this is the actual overall architecture. Also, is this too small by any chance?
Yeah.
Oh, I'm sorry. Okay. Anyway, I'll circle it. Okay. So you have your encoder, right? You're getting your tokens, right? And then we're going to have a 3D patchification, which is basically we're saying, okay, this is our image, right? So we're going to have I by I by C. And then we're going to basically go ahead and we're going to scale it down by PT, PH, and PH. So basically we're taking our image and we're just basically taking every single block and then we're just downsampling it. And then they were just going to flatten it to a single basically input tensor. Make sense?
Weren't we already in token space, so we're just compressing we're just downsampling the tokens even further?
Yes. So downsampling further, and then you're taking and you're actually flattening them into one single input vector. Yeah. So you have your tokens, right? Right now, think of it as you have your image, right? And your tokens are going to be in a cube, like this, right? So what we're going to do is let's see, linear flat and 1D. Okay, so we're going to take this cube we're going to take these patches of size PT, PH, PW, going to pass them through a linear layer, and then we're going to flatten it. Q is where? Cube. Oh, those are the output tokens. Those are the tokens. So through your encoder, you get tokens. And they're still going to be in 3D.
So you have input a video.
Yes. Because if you remember how the output of this, right, this is what you're working with, right? These are your video frames. The output is going to be these guys, right? So they're still preserving like the temporal features, right? You still have like the first compressed video frame, the second, and so on and so on. So now we're going to take that and we're going to take and basically flatten it while preserving some of the spatial information.
Why is it a cube? What is that cube?
I think that's just how they represent it. Like if you look at the output, do I have the output dimension? No, I don't. But again, the whole point is that each one of these, right? So you can think of it as a cube, right? Because like every single one of these is, in this case, like you have your, I don't even know what that is. Epsilon. Let's say it's epsilon. I don't think it's an epsilon. Okay. Anyway, so you have this, right? And that's basically the encoding from a single frame, right? And then you have the next one, which is the next frame, right? And every single one of these, they'll have like their own. I don't know why. They'll have like their own, like basically. That's a good question. Why is it a cube? I don't know. I just think of it just like tokens, basically. Like just I don't know why they chose a cube. I think just like to show like you take your image and then you're basically converting it into a set of tokens that are both spatial and width and like image wise. Okay. So now let's see. Again, so we have our patchified image, right? We compress again. If that was a little bit confusing, think of this. We have a set of tokens that represent our video, right? Just start at that point if you're like confused about what happened before this. We have a set of tokens that represent our video, and then now we're going to apply rope across every single dimension, right? So rope is basically positional encoding, right? Similar to just like a transformer, right? So you just like sine and cosine, but here's just a little bit smarter. And we're going to apply that across every single dimension. Right, so independently. We want to basically have positional dependence across the height, width, and time dimensions. And then another cool thing that I found was that actually, again, if you think about it, if you have a video at 30 FPS versus a video at 60 FPS, right, you have to make sure that your scale is the same. Right, so if it's 60 FPS, you're going to like drop every other frame, to make sure your input is the same. And then finally, they're also going to tack on an absolute positional embedding, which is just like something it's a positional, think of it as a positional encoding that you can back propagate and learn, right? So if the model learns that, okay, I really need to attend to like the first image frame, right? Then it will basically have the information in that absolute positional embedding. Cool. Now, again, we have our image, right? So now, but also we want to condition on text, right? So we're going to, if I say cross attention, do people know what that means?
Is that something different than self-attention?
Yes. So in self-attention, you have, so again, attention, you have your query, key, and values, right? Query is the information that you're looking for. Key is the information that you have, and values are actual information you contain, right? So in this case, the queries are coming from you, right? So you're saying, okay, you're trying to basically condition on external information, right? The external information will provide you with the key pairs and the value pairs, right? So key is the information that I have, values information, while you're giving the queries. Right? The easiest way of thinking of it is like a translation task. Right? Think I'm going from like English to Spanish. Right? I fed my English sentence into my encoder. Right? And then after that, I start generation of my Spanish words. Right? And then I'm going to start off and saying, okay, I don't know. Like, let's say I'm translating like I like coffee. Right? Right? We're going to start off by saying, okay, these. Let's just say it's just like this is my tokens. Right? Just to make life simple. Right? And we're saying, okay, when I start generation, right, after saying yo is I in Spanish, right? After I output yo, right, I want to start basically cross-attending. Yo will generate the query vectors, the information that it wants to attend to, while the values and the keys will come from this sentence, right? And that basically allows you to like add on additional information on top of your transformer, right? And then finally, I'll talk about the rescaling later on. And the whole point is that like actually cross attention, I think my next slide talks. Yeah. Okay. So this is basically the trade-off that they went through. So whenever you're trying to condition a transformer on additional input, you have three basic options. The first is just in-context conditioning, right? So if let me get on your page. What even is this? Is DuckDuckGo owned by Google? Okay, cool. Okay. Okay. So anyway, so we have three things, right? So now let's think of it like in terms of robotics context, right? So let's just say I feed my LLM, right? So I feed my LLM like a sentence, like move the cup, right? And then additionally, I want it to also know what the robot's joints are, right? So I feed the LLM the text, and then additionally want to also to know the positions of the rope with actual joints of the arm, let's just say, for example, right? So the first option is, okay, what if I just like, if a Q denotes joints, right? What if I just tack on the joints as part of my input, right? And that is what is in context as conditioning, right? But this paper found that in context conditioning actually performs pretty poorly, right? The next thing I can do is that, okay, what if instead of in context conditioning, I still only feed this, right? But then on top of that, during the actual calculation, yeah.
What is the metric on the y-axis?
The y-axis is. This screenshot is from a diffusion transformer, but I think it's like image quality. I'm not too sure, but lower is better. Lower is better. Yeah, good question. I should have. I'll keep that in mind later. So the whole point is, okay, cross attention is, if you remember, right, okay, what if, I keep this, but then on top of that, I'll have like basically another separate encoder to encode my Q, right, and then it'll come in with, again, queries come from the sentence, right, and then here I'll give the keys and the values, right, but the problem with this is that, okay, I have a massive compute overhead. I have to train it's way more expensive to train. And the question that DIT asks, is there something that is more, can we basically achieve the efficiency of in-context conditioning with the performance of cross-attention? And the answer is yes. They came up with adaptive layer normalization. Are there any questions at all? That was an excuse to drink some water because my throat was dying. Anyway, okay. So as a review, layer norm, right? We have our input X, right? Input, think of it as this. Like X is just like a single image frame, right? And what we're going to do is that we're going to normalize it by the average, basically just normalization, right? We're going to find the mean of X divided by standard deviation. And on top of that, we're going to have two learnable parameters, gamma and beta. Right? And now what layer norm proposes is that, okay, instead of just, having these learnable parameters as just by themselves, like just single, basically, single neurons, is it neurons or is it single weights, instead we're going to learn them from an MLP that's conditioned on, okay, let me also clarify. T and C, in this case, T is like, think of like the time step of our diffusion, right? Like, I'm telling you, I'm on like the teeth step in the diffusion process, right? While C is, let's say I told to generate an image of a class, right? That's like the external information that we're providing here. Sorry, I should have clarified that. I think also like I had them stated here, but then I added this equation in and like they were deleted. But then, okay, so think about it this way. During a diffusion process of an image, right, we have our tokens, right? T1, T2, right? Oh, tokens, T is a horrible name. T1 to 3, 2, right? And then additionally, we want to condition on external information. One external information is the time step during our diffusion, right? Because if you remember, we have to go from time step 0, which is pure noise, to time step xt, right? X0 pure noise, xt, which is our output image, right? So we're going to go ahead and we're going to condition on just we're going to add on like the time step because that's important information, right? Finally, we're going to say, okay, I want you to generate an image of a class, right? And let's say we have a class of a cat, right? So this is like our external information that we're tack on. And what we're going to do is that we're going to take this information, we're going to concatenate it, and we're going to feed it through an MLP, right? And that is how we're going to get this gamma and beta out of this. On top of this, you'll see the next slide, we'll also get a third parameter, alpha, that's used for scaling. And then basically this is how it will look like. This is where the scale and shift come from. I'll get back to you in a bit. So at every single layer, again, this might be looking scary, but again, think of this. These are our images, right? We patchify them, we flatten them, right? And then here, this is our external space, right? So our label Y and our time step T of the diffusion process. And we're going to pass that through an MLP every single time. And at every single step of these N blocks, we're going to basically use them as normalizers of scaling. And you think of it as like a way of adjusting, right? So, like, let's just say I'm generating an image of a cat. So I'm going to shift my weights towards like a space of a cat every single time, at every single step. And this basically was shown to be more efficient. Why it works, they didn't explain it. They just tried it out and it worked. Jina, you had a question?
Yeah, two questions actually. One, MLP, again they're plugging in an MLP. Why does this work? How do they train them?
I did not look into like how they trained it. Like I think it's just standard backprop.
But like, with respect to what? How do you know why and beta optimal?
Because I think I'm a little bit. I don't think I'm understanding your question because my answer to that would have been like they're just like part of like the backpropagation process. Like because like.
But then they're saying that no, instead of learning like gamma beta as part of backprop, we are going to make an MLP output the gamma and beta, and now.
Well, that's part of your architecture, because your MLP, you backpropagate through gamma and beta as well.
Oh, okay.
Yeah. So like this is like, again, like look. So what's happening is that, like, you're still normalizing your input, right? But then on top of that, you're scaling it by gamma and beta. But then during the backwards propagation, the loss will also backpropagate through the MLP.
Okay, got it. So they're trained in tandem. Okay.
Yeah,
Understood.
and then same thing with like you get like this like alpha scale parameter, right? It's just a way of just like learning basically like constants to basically change the like which way you're diffusing basically, if that makes sense. Okay.
Yeah.
Okay. So now, what if I say LoRa? Yeah, sorry.
One more question though. The continuous tokenizer. How do you apply positional encoding? I see 3D rope is applied.
Yeah.
And absolute positional encoding. That in slide 21.
Yeah. So that's a good question. That was one of the things that I didn't understand, because like what's happening here is, where is this? Continuous slide 21. Yeah. So the whole point, what I understand is like, why do you like first flatten it and then apply it? But like that, I did not understand that, because like for me it would make sense. I'll keep the spatial representation, apply the positional encoding on the spatial the representation that has space, and then flatten it. But I think like basically I don't know why they just like flatten it and then apply it, which I guess like is the same, because flattening is gonna like you just have to like be a little bit smarter.
Okay.
Yeah.
But why do we have multiple positional embeddings? Why is there absolute positional as well as 3D row?
Yeah, so 3D is just like you just tack it on, just compute it, right? While absolute is like basically trainable. So like if you want to attend to like, as the model wants to learn to attend to something else, it'll learn to like, okay, I have to focus on this part of the image.
Okay, but so it's focus. But we're adding two positional.
Yes,
embeddings.
absolute and rope.
Okay.
Nice. Okay, so that makes sense. Okay, so now finally, like again, we tacked on like this MLP. We tacked on n of them, right? This is going to give us additional computational overhead, so we're going to use LoRa. Do we know what LoRa is? When I say LoRa, does that? Okay, I'm just going to quickly go over it. So LoRa is basically, if you have a matrix like saying mass like n by m, right? Sorry. Thank you. I appreciate it. So you have like n by m matrix. What we're going to do is that we're going to decompose it into a multiplication of two matrices of smaller ranks, right? So instead of learning n by m, I'm going to learn n by 2 matrix, right? And then also learn a 2 by m matrix, right? So when I multiply these together, right, you'll still get an n by m matrix, right? But now you have to learn significantly less weights. And that's basically what it does. And like this is super helpful. Like if you're like doing like any like fine tuning of a LM like Llama, you're going to use LoRa, because none of us have that compute lying around. Okay, I guess and I'm gonna maybe go a little bit faster. But basically, again, they go ahead and they train it. So they train it to be like, first you give it text, and then you generate it, and then you condition it on generating. You give it text, it generates an image, and then you condition. Okay, here's text, here's image frames, generate the next image frame. And then basically this is the result that you get. And it's pretty good. It's pretty good. They have, but again, the whole point is that this is a 7 billion parameter model. So my guess is that they probably want to deploy this on a Jetson, which will be sick. Like think of a robot that's like moving around a warehouse, and it can like, okay, like if I turn left, I'll like hit something, right? And it can like predict that. I'm going to skip the autoregressive one just for time constraints, and I want to focus on post-training. So think about it this way. Like we have these pre-trained LLMs, right? Now we actually want them to be pre-trained world foundation models, right? Now we actually want them to be useful, right? The story of like every AI company out there. Okay, anyway, so there's 3 basic tasks that we can do. The first is instruction-based video prediction, where, think about it this way. You're trying to actually generate data. Right, so you go ahead and you say, okay, here's the current video frame. Here is the text instruction, right? Please generate the future, right? So in this case, the input frame was this, and you're saying, okay, show me a video of a robot organizing books by placing them vertically on a shelf, right? Another application you can do is called action-based next frame prediction, which here, what you're saying is, okay, here is the current video frame, right? And again, we can also condition on additional details, right? So like how the ADA-LN layers, they condition on T and C. Well, we can also condition on things such as like a robot trajectory, right? And it's going to be very computationally efficient, right? So in this case, you're given the current frame and an action vector. And an action vector, why did I had an action, oh, okay, there it is. Okay, nice. I was confused. Okay, so basically it's like your action vector, right? So like, these are the changes that I want my end effector, and you're going to generate being the next frame. And the fun thing here is like this. I did not know how they did this, but I looked into it. Like basically, they work with 1X, which is another robotics company, and they actually collected like 200 hours of like a robot performing a task. And then they go ahead and they took that task and they basically trained on top of like this high quality data, right? So this is what I mean by like high quality and low quality, right? You have like 20 million hours of low quality data and just great, like, like here's like a guy like driving a car, right? And then you make sure your model is good at this, right? It's a good generalist model. And then you say, okay, now here's only 200 hours of a robot of a task specific data. And then you're going to basically fine tune it. And the results are pretty good. So here, again, yeah.
Wait, can you run the yeah, so for like the the action-based next frame prediction, it was only post-trained on like the specific ARM data set, nothing else, basically.
Yes.
Okay.
In this case, the bridge data set.
Okay.
So again, the whole point is that you train on a lot of data rather than to actually get good at a specific task. You're training on like a smaller set.
Well, this bridge data set was created by like the 1X robotics.
A bridge data set exists. I was talking about 200 hours of Eve.
Oh, okay.
Yeah. The results are pretty good. So actually, well, I don't know. I have kind of like a stupid comparison because they're saying, oh yeah, like we ranked it internally and like we found that Cosmos was better. So like, basically, what they say, like they flashed a user with like they basically had a study where like they showed people like a frame of Cosmos and like basically an example that Cosmos gave, an example that in this case Video LDM gave, which is like another baseline, and they said like, oh yeah, actually like we liked our examples better. But I don't think that's actually a good metric because, like, they didn't talk about a lot how they actually did it. Yeah. So, and then here again, these are just like some additional metrics of the actual generator, and it's pretty good. So yeah, that's basically all I had. I want to make sure we're out of here on time at 9. So that if you want, I could also like talk about the autoaggressive one, but like in reality, like the diffusion one is far more interesting. So yeah, thank you guys for coming.